connected to the Indian freedom struggle and the country's progress. From a very humble beginning, we now have several department centers and school, more than 50 in total. And most of those are very relevant to the present context. For example, starting from the computational and data science, where our Param Shakti system is one of the feather in our cap, strengthen the computational research significantly. We also have other centers like Center of Safety, Center of Defense, Center of Aerospace, Kalpana Chawla Space Center, and a variety, Center of AI ML also. So all are very relevant actually to the present time. We have more than 16,000 students, about 800 faculty members, and 1,000 staffs. We work in a variety of fields. You all may know about it. And more importantly, we have a very vast campus also, 8.7 square kilometer big campus, a green campus. So whenever you get some time in between, catch hold of a bicycle and just have a go through our beautiful campus and enjoy your time over here. So with this, I appreciate the effort being put forward by Professor Shomajit, Professor Somnabda, and Professor Rakkaraju and Professor Ashok De for this organizing this workshop on CFD. And I inaugurate the program and welcome you all once again. Thank you.
So I give it over to Professor Somnath. So we'll coordinate this event further.
Yeah. Thank you, Professor Chakrabarti and Professor De for inaugurating the workshop. We have our resource persons, Professor Ashoke De, who is an Air Force Chair Professor in the Department of Aerospace Engineering and jointly with Department of Sustainable Energy Engineering at IIT Kanpur. So he is also Associate Dean of Academic Affairs there. Professor De is an expert of computational fluid dynamics, and he works in different areas across multiphase modeling, computational aeroacoustics, hypersonic flow, energy harvesting, fluid structure interaction, etc. He has a very long academic and industrial career in computational fluid dynamics area, worked in several academic institutes as well as industries. And we also have Professor Rajaram Lakaraju from IIT Kharagpur. Professor Raja Lakaraju is a faculty member in Department of Mechanical Engineering, IIT Kharagpur. He is teaching several courses in the area of computational methods with application to thermal engineering, multi-phase flows, wave mechanics, etc. His research directions are in turbulent multi-phase flows, geophysical flows, and he is also applying machine learning and trying to couple it with computational fluid dynamics simulation. So they will be the resource persons. Along with them, we have our teaching assistants, few in doing the hands-on labs. Hello. So hello. So our teaching assistants are Snehal, Anurag, and Prasenjit and Devajyati. So they will be here to help you how to access the system, how to start working with OpenFOAM. And whoever are attending online also will provide some access to some of the supercomputing nodes at IIT Kharagpur, in which you can log on remotely and work also. Also, our teaching assistants will help you to learn how you can install OpenFOAM in your system and start at least do some of the basic works there. Some initial calculations you can do there, and then you can log on to the system in some of the lab sessions. So this is very important both for offline and online attendees, that please listen to the instructors during the hands-on session, because as this workshop is termed, it's a hands-on workshop and you need to learn by doing it. Only going through the lectures is probably not the right thing for this workshop. as well as for the online attendees, you please tell when you are facing issues with connectivity or missing certain things, or you have some confusions, please raise your hand through the Teams or write in the chat window so that we can look into it frequently and try to resolve it what is happening. So please attend the instructions very carefully, so that at the initial phase there will be some lags due to not understanding some or due to some of the communication issues, or not understanding clearly how to install OpenFOAM or start working with OpenFOAM. Maybe some of you already have some introduction to that, but for the beginners there might be some hiccups. Please bear with us, and whenever you are facing problems, either verbally or by raising your hand for online candidates or putting it in the chat window, let our instructors know that what are the issues, because if you fall back in the subsequent sessions it will be difficult. Okay, so we'll disperse for a while now and go for snacks, and then we'll come back and start the sessions, regular sessions. Thank you all. Where is the schedule? Next session kota theke? Yeah. So in 15 minutes we'll get back and start the sessions. So online attendees, in 10 we'll start the technical sessions. Thank you.
Hale. Hale. Hello, hello. Can you hear us? Let them check the other room. Online participants, if I'm audible, can you just drop a message? Okay. So I'm audible to everyone. Hello, hello. Am I audible? Online participants? Can you
Yes,
type
yes.
some? Okay, perfect, perfect. Yeah, we'll start soon. I'll just. Okay, good morning, all. I think. Okay. So, online participants, I am audible, right? Okay, and the screen is also visible. So, okay, good morning. So let's start with the first session uh, on this particular workshop. So what the plan is there, it's a bit lengthy session. So feel relaxed. If you have a question in between, feel free to ask me. Okay. And so what I would like to go over in this particular session, covering few basics, just to give you just how many of you have done CFD? Okay, good. So I think then the basics would not take too long. We'll just quickly refresh the things, and then I'll touch some of the HPC related issues. That would be somehow bit, and then talking about parallelization before we get into the OpenFOAM. So anyway, the OpenFOAM thing also, we have a follow-up hands-on session where some of the basic installation issues or command and the structure and all these, that would again going to be discussed. Okay, so let's start with the basics. So what is that CFD is for? CFD right now has been kind of a tool which has matured enough, which can solve your day in, day out problems. So in fact, I would say that this could be a basket of under the bigger computational tool or CAE, and CFD is part of that. CAE can have your, let's say, the structural analysis, can have molecular dynamics, you can magnetohydrodynamics, all these can be a part of your CAE tools, and CFD is one of that. So which allows you to solve all these large scale daily life problems, which can be handled with this particular tool, where you have, I mean, obviously you bring in the programming and things like that. So how you go about it, you have essentially a fluid flow problem in hand, which is a practical problem. Let's say you in hand, so you need to find out the problem. I mean, once you have it, how you, so any problem like that, they are usually governed by certain governing equations or the conservation law. So you need to identify those things, which I kind of term it as a physics of fluid, so that you get to see uh, effectively the governing equation. Then you identify the set of equations, typically the conservation laws in terms of mass conservation, momentum conservations, energy conservations, species mass transfer conservations, angular momentum, whatever is required to kind of define your problem to solve. Then from here, you apply your numerical methods. So this could be anything. So you apply your numerical methods, namely like you apply finite difference, finite volume, spectral, all different kinds of method that would dictate what you get the mathematical form of the system. So this mathematical form that you obtain, then you couple that with your physical geometry, which in terms of grid, then you convert that to a programming language and feed that set of instruction to the computer program, which you get it a full complete solver, which would solve the system for you. And then you get the results. And finally, once you analyze the result, it should close down the circle and get the solution of the fluid flow problem. So that's essentially the component of CFD. Now, if I look at the stages that I have to go through this CFD, there are three primarily important stages. One is the pre-processing. Pre-processing stage is something where you define the geometry, you identify the model, physical model, and then try to have the grid and all these ready. These are done in the pre-processing stage. Then the processing stage, something where you do the computation. That means the problem that you have set it up, you convert to the mathematical problem, and then through the computer program set of commands, you send it to your computer, who is essentially will do the work for you. So if you send a wrong set of commands, computer is going to give you all junk for you. So this is where, and then finally you try to visualize the data. So since you have some background of this idea about this whole process, and this becomes an iterative process. So once you see the results, you try to extract out the physical interpretation out of that, and then if it doesn't work out, then you can go back and fine tune things. Now, which of these components usually take the major time of, let's say, if I have to divide the complete time frame of the skill in 100%, what is your guess that which stages take how much of the percentage of the time? Any guess? So is the processing, pre-processing, post-processing, which is the most time consuming component of it? Huh?
Pre-processing, sir.
Computing, right? So anybody else? Any other taker with other? We can have three options. So one of that, so I think by and large people are taking the middle one. So there is any other taker? So the thing is that you are slightly off from the system. This guy takes the most of the time rather than computing. This is what the beauty of the whole process. Computing today's time is not the headache. I have so much of architecture, which is highly computing power I have in hand. Pre-processing, post-processing usually take the bulk of the load. 60 to 70% of the time goes there, not in the processing. Processing is much more, I would say the calm element of this whole process. This takes a lot of the time because if you define a geometry wrongly, this guy is going to give you all junk. So it essentially becomes a very classical thing, which I have a very, I am also very passionate of that. I have that slide here also. I'll come to that, what it can do. Now, effectively, what you can see here, you have the tool which is ready, which can solve the problem for you. Any problem that the practical problem that you have in hand. The result, once you analyze, it will give you some kind of a interpretation. Once you interpret that, then you can actually have an option to analyze it, then go back. And then finally, this should becomes your a pathway to the design consideration. So today's day in the big manufacturing industries or this has become a design tool, the CAE, computer aided analysis. And CFD is one component, which includes, as I said, the CA tool would include your structural analysis, other analysis. This becomes the tool to go for your design process. The reason, because it could save your time, it could save your cost, it could save your manpower, it could save a lot of things. But yes, one of the things is that you can have your analysis, the time frame, hazard issues. So if I try to compare here, it's a cost effective, number one. Number two, time to get the result out is very short. So I can go back and fine tune and get back the data again. Scale, I can do any scale of simulation today's date. Information, I have the complete spectrum, because sometimes if I go to a complicated, let's say if I talk about the my four-wheeler or the aircraft engine, even in the in-depth experiment is not possible. But here I can get the every bits and piece of information inside that. So, and it's also safe. Now, every industry, they would like to save that $1 million by investing, so that it has become an, I mean, don't have that wrong concept of that, okay, CFD is going to compute with the experiment, or not like that. They should go hand to hand each other. If I only do some calculations, have my design ready, go for fabrication, testing, error, go back, it is going to cost my time, money involved. It's a $1 million business. Nobody would like to do that. You get the first cut done, you have some initial prototype ready, get the CFD analysis done, go for testing and all these things. So do that, come back, rectify, so that your design ready, go for final model prototype and go for production. So it reduces the time frame. So this is what the CFD has become. Now, why computing is taking less time? This is not 70s or 80s where even your mainframe computer would not be able to do, but your laptop, what you are using today, could do a lot. Even if somebody is using like Apple MacBook, which has the GPU also. I mean, M2 has 8 or 10 core GPUs, which can do a lot of things. So some reasonable amount of problem or size of problem we can even solve in our laptop today, which was not possible. And the important component is that the architecture that we have today, we can do a lot of floating point calculations. So that means which are termed like a flops. So the machine that you have, which can give you, so the computing power actually increases very rapidly. Okay. So if I sum up that whole process, you have a problem to solve. You identify the problem, define your governing systems and all this. You make the pre-processing stage, all the calculation that you are supposed to do and things like that. Feed that to your model setting and execution of the computer program. Finally, the analysis and all this, so that close down the whole circle. But yes, CFD is only a tool. You as a scientist or engineer, you have to use your brain. If you send a wrong set of command to a computer will only give you the wrong set of answer. So computer, you can think about like an bull for you. Whatever you instruct the computer to do, it will do the job for you. If you send wrong set of things, so you have to be there. So you have to comprehend the problem physically. You have to identify the challenges associated with it. You have to kind of feed the correct set of or piece of information. So this is what already you have talked about, your pre-processing stage, where you set up the grid, then you send it to the machines, and then post-processing you analyze the data. So obviously, just quickly to get into that, when you identify the governing equations and this, you apply the numerical method to get the system which can be programmed, and the method could be of different types: finite difference, finite element, spectral, lattice Boltzmann, finite volume. This should have a different range of solvers. So whatever numerical methods that you adopt and apply, it's going to give you finally, or at the end of the day, it's going to give you a set of mathematical problem, which you need to convert through a programming. You convert it to a executable system for your computer. So if we just quickly see what you have these days, you have a lot of open source which are available. I mean, one can explore. Obviously, there are some big players in the commercial packages like Fluent. I mean, I need to update that. Fluent, CFX, everything's now the under same ANSYS. Star CCM is another one, COMSOL multiphysics. So every package has their different kind of solvers. They have their different capabilities. They can do, I mean, it's once you start exploring, but the whole point is that then people in academia, some industry, they have their own in-house solvers. Then there are open source code. OpenFOAM is one of that. Probably we are gathered here to look at that. There are other open source solvers also. If you explore today in the internet, you get plenty of things. But again, you have to use your judgment, use your understanding to do that. So one can definitely explore things. So obviously, these are advantages and some of the limitations, because end of the day, you have to keep one thing in mind. You are adopting some approach which is essentially numerical approximation. So there would be error which is associated with it. There would be error. When we talk about error, it could be in terms of human error. It could be in terms of system error. It could be in terms of numerical error. So it could be in any type of error. If you, as I said, boundary condition is another key component of all this. If you set wrong set of boundary condition, it's going to give you again the wrong set of data. Obviously, these are things one has to take care, and just which area or where is this not being used today. It is used in every industry pretty much. Whatever I could think about, list can be more than that. If I have missed anything here, you see that any industry pretty much, including even biomedical, sports medicines and all these things, everywhere now these days CFD is being used, heavily used. And where it is used as a design tool. So this is the level of maturity that you have. Now, as I said, if you don't use your judgment, if you don't use your understanding, if you don't use your, I would say, the competence level, the CFD, which is supposed to be a computational fluid dynamics, it can become really colorful fluid dynamics. So now it is up to you whether you really want a colorful fluid dynamics or not. And there are some saying by these great people who are no more alive today. So you can do whatever you are doing. You could be the believer of that. Nobody else would believe you, things like that. But these are something which that's why I said this is one of the slide which I like the most. So whether you like it or not, but eventually what George Fox said, that essentially all models are wrong. Nothing is there. So some are useful. Thing is that with that note, what I would like to convey the message is that there is no free meal in this world. What you do, you have to pay the price for it. If you make a small error, it can propagate or cascade to a different set of error which will show up. So your competence, understanding, comprehension, these are equally important, though you have a very robust tool in your hand. So the human intervention or involvement is not going to be, obviously one can counter argue that, okay, I have artificial intelligence, artificial robots. Yes, you can do, but there is a limit to it. As I said, that also doesn't come free of cost. So something or the other would be price that you have to pay. Okay, so now we'll go to the HPC, because this is the component which would be connected with your, essentially your computing part. Now, what is HPC? We all talk about, oh, I'm doing this, I'm doing that. HPC is nothing but a set of computers. Even if you have all the laptops, if I connect them, somehow manage to connect them together, and I can use the resources that you have, let's say 30, 40 computers sitting here, then I can do that, all these laptops for a single job to do the calculations, but using the individual resources that you have. So that means what I'm trying to do, I'm trying to propagate the whole problem, or rather divide the problem in, let's say 30 more computers to do that things. So, and that goes in at the same time in tandem fashion. So I can get the results done very quickly. So supercomputers are like that only. You have a set of computers, individual computers, which are somehow connected them together. Now, how they are connected, that's a separate issue. Okay, they are physically connected, definitely. They are not virtually connected. But obviously, the way you can immediately think about they're connected by the gigabyte LANs, no, those days are over. Probably early 2000 used to be connected like that. I cannot connect these machines without having any optical fiber these days. If I do that, it's just like you can think about in a simple way. I have 40 laptops here. If I connect them together and ask them to do the same command, let's say x plus y equals to 2 to solve, do you think all the computers are going to perform in the same fashion, is going to give me the results in the same time? No. Why? Because the architectures are different. So that means immediately that depends on what architecture you have. And then I would say that I will go one step further. I would say that I want to solve x square plus y square, but then I would like to find out the x square plus y square, but x plus y equals to 2, y minus x equals to 4, something like that. And these two equation, I would send it to all the computers, let them solve it, get me back. Then I would compute in the other side, the x square plus y square. So x plus y equals to 2, y minus x equals to 4, whatever is that I have sent those two equation to all your laptops. Then in getting the information back, x and y, and then doing the x square plus y square for full domain. I mean, assume a big computational domain, things like that. So x and y, which would come back, the value of x and y would come back at the same. That's not the question, because that cannot be wrong. That would come back same, but they would come back at a different time, because every computer is performing at a different level. Their performance level is dictated by the architecture that you have. So that means, let's say x giving me back xy value. So I have divided the domain in multiple sets, and let's say this segment xy value comes from here, this segment from y, third segment from z, this for a. This guy get it in one particular time frame, this guy will get it from another time frame, this guy will get it another time frame, because they are sending it back at the different time, because their execution time is different. Now, once that happens, so let's say this bigger block where I'm supposed to calculate x square plus y square for each of these points, I'm not be able to do it at the same time. Or if I want to do that, I have to wait when all of them gives me back at the higher level. So this is where you lag time in communication. So when you talk about HPC, this level, what I am doing, this is the floating point calculation or operation. This is fast enough. But now still you have a bottleneck communicating to the other guy. So the communication also in another bottleneck or another issue that one has to resolve. If you really want your HPC system to perform really at a faster rate, this communication has to be fast enough. So how you kind of reduce this communication error, that is another thing. So once you talk about this communication and also execution of this process, one of the important component that would be there is the how you send this master command to all these things to execute that x plus y and solve that equations, that through the parallelization process. So obviously this what I have already talked about, that since you cannot do in your regular scale of computers, you need this HPC system. So the high performance computing systems, which are, you can go to this wiki there. So they call it how this was the first Cray system, which was introduced in 1960. I mean, just to give you an idea from where we have come now. And today we can do the flops calculation, which is in not even tera, zeta flops. This is the flops 10 to the power 21. That means that many floating point operation you can do per second. So that's the change in architecture. So what this is a real challenge for even a CFD engineer, how you scale your code to that kind of operation to, I mean, even petaflop, teraflop is quite huge. It's not every solver, every code can scale to that. And to scale that floating point operation to that level, one key component is that a parallelize. How you parallelize these things. That means how you send the set of commands to those individual set of laptops or computer. Okay, execute this. So that becomes important. So already I have said that the communication is one of the issue that you have, which is going to create trouble. At the same time, you have these parallelization issues. So if you don't take care of the parallelization efficiently, what effectively you are going to lose out time in all this process. So that means you might look at, oh, total execution time could be 3 minutes. Out of that, probably you have waited a long to get the information back from your subnodes or subcomputers. So parallelization, communication, these are issues. So more and more you have development in the architecture, more and more you go towards the high end of computing power resources. It also brings in the challenges with the parallelization issues, challenges with the communication issues, which you need to kind of handle it. Okay. So this is how typically the architecture, how it looks like. There is a one which is there probably during your lab session, you will be connecting the whole machine is there. From the outside, probably you might be allowed to see. Inside, I don't think whether you would be allowed to go it in, but the computers are set like this. This is an Argonne National Laboratory computer, IBM Blues in, but typically they look like that. And the set of you are sitting here as the user, this top level, and you see that the down level, what is happening? There is a different layer of architectures or the issues which goes in set of commands in terms of or whatever. So you are here without understanding through your terminal. Okay, you are just connecting that setting, sending the set of commands, trying to execute something. But things are happening at that level and then coming back. So everywhere you come back, you send a set of commands, receive a command back, there would be a time lag. So that's a latency effect. So you lose those information. Even in the computer architecture that happens. So there are people in the computer science who have been working on that, how you reduce that, make it much more efficient. So every time you send a piece of command and get a receive another piece of command back, there would be an impact on that. So not, as I said, nothing is free. So if you look at this list was from November, I think they supposed to make another list out. So quarterly they make a list out. You see the demographic distribution of this, where the top 500 computers, and it can span over different kind of applications. So you can go to this site out of our curiosity and look at those big computers. And these are some first 5-6 computer and see their flops calculations, what are these, and the number of ports are different issue. So that is the floating point operation they can do. So it's a huge computers. And the interesting part is that by 2025, this is the projection how the computer power or performance is going to go. Fairly linear, so it is kind of scaling very rapidly. So that means your architecture development, architecture innovation is going very fast. So it just like if you see the scale in the axis, it's almost a factor of roughly a 10 in every 4 years. That means that becomes a challenge for a CFD engineer or CAE engineer. How can I make my code or solver to be compatible with this kind of high-end architecture? Because that's a different challenge. So that means every time you cannot be relaxing. Oh, I have a solver which is ready, can do a lot. Tomorrow probably you become obsolete. Maybe 3 years down the line you become completely obsolete. That is not at all going to work because the architecture is going to change and you will be out from the business. So this gives you different challenge. So computer scientists who are working or the chip scientists who are working on the computer chips and all these things, they are throwing you back a different challenge. These are where Indian status as of now. So we have few which are one is within the 100 list, but then we have few in the top 500, but at least none of the academic institutions featuring in that list. I mean, 3 of them in Indian meteorology, one is in the CDAC. So what this HPC does for you? it's a throughput. What it does, it essentially what I said that what your single computer can not do, you try to distribute that send of command or operation in multiple computer. So you try to basically reduce your time frame of the operation. And how effectively you do that, you get your results show quick. So different machine will have different throughput, which we already kind of by an example. So effectively what is there, the text we have already kind of talked about it by through the example. So same thing is written there. So what you can do in few hours of time, you want to reduce it to few millisecond. So how does the HPC increases the performance? Obviously, single computer is not good enough. Let's say I have a million grid points to solve. If I put it in one laptop, it will slow down. It will run for 5 days. So I would like to distribute over 40 laptops. Now, if I do it evenly distribution, probably I would minimize the time. If I don't do that evenly, let's say some laptop will have 10,000, some will have 5,000, some will have 15,000 grid points to solve. Obviously, again, I lose out time in communication. Who is doing 5,000, he will do fast, he will wait. Other one who is doing 10,000, he will go slow. He will send back the communication, and I have to receive all communication together and then execute the next level of operation. So every stage it is. So that where you need to have the parallel algorithm in place. So that means you should have an set of instruction which would make sure that the operation that you do in these individual computers, you try to do at the same amount of time, assuming you have the similar architecture in place. If the first hand I have all different laptops in sitting in place, no matter how effectively you do this part, you're not going to get the things out at the same time. So assuming that factor in place, that I have all the laptops are of same architecture, operating systems are same, then I'm to get the information back at the same time when I send the information in an evenly distribution file. Okay. So how do you do that parallelization? What are the issues with the parallelization or the basic step that you have with the parallelization? Any questions so far? Yeah. Yeah. Hmm? No, first hand the problem definition is not correct. As soon as you say that I want to do 4 different problems, that's not the idea here. Here, you have one problem in hand, which you would like to execute in parallel fashion. If you say 4 different problems, the game is different. So you cannot change the rule of the game. That's a different issue altogether. Here you talk about I have one problem in hand, whether I'll do it in one computer or do it in 4 different computers. That's probably ideally the question to be posed. Obviously, 4 different computers, if I divide, I will get the faster turnaround time. 4 different problems, different issues. Now 4 different problems. Okay, the issue which is a little bit connected to the parallelization, since you raised it. Now I'll come back to your second part of the problem and modify the question. 4 different problem, I push it to one computer. 4 different problem, again I divide into the 4 computer. What do you think? Which is going to give you the output in quick time? Huh? Second one. When you push the 4 problem, assuming the same size of problem, same number of grid points, everything in one computer, you are loading that computer. Why you are loading that computer is it has only particular number of processors. For example, if I talk about your terminal these days, i7, i11, i13, there are 4 processors. So again, I am assuming that you are smart enough to push the 4 problem in 4 different processors, right? Through some scheduler, something like that. So if I push it to 4 different processor, that means individually each processor is doing the job in that one particular i13. Still the time frame would be higher. And the issue here is that every processor is loaded with the job, and what they are using is the one single memory that you have in the system. So one hand you are doing only you are only trying to do the floating point operation, but top of that you have the memory which has to be used. Then there is an L3 cache of the architecture. Okay. So for that particular machine, these are fixed, and I'm trying to use it for 4 different jobs by 4 different processors. So they are going to face the same memory. Obviously, there has to be also some delay in the latency. So you lose out the time in those issues. Other worst scenario, which is probably the worst of the worst. I don't have scheduler. I'm not smart enough. I'm just blindly push that 4 problems in one i13 machine. All the 4 processor would be used in a random fashion, and you don't have any control over it. Then it is going to be much more, I would say, messed up condition. Okay. So I was about to come to that just right after this worst example. So probably that situation is probably the most worst condition that ever one would like to have. You don't want that. So you should have some scheduler, something like that. So at least safeguard the process, make sure individual processor doing one individual problem. And next level to that, the 4 problem, I'll push it in 4 different computers. That means one problem is handled by one computer. He is using that much of memory and cache I have, then obviously the execution would be faster. So I would get quick runout. Reversing the wheel. Again, I come back to single computer. Okay. Now I forget about 4 different problems, which is connected to this online question. I have one problem to solve. I'll just push the problem to that computer. Let's say that i13 having 4 processor. And if you do hyper-threading, it can be done up to 8 processor. So I can push it to 4 processor. It will do the job. I can do the same problem, push it to 8 processor by the hyper-threading. One single computer, same amount of memory, defined problem. I just do it in a different way. One hand I will push it to 4 processor. Other case I'll push it to the 8 processor. What do you think? Which one is going to take more time? Any guess? 4 processor or 8 processor? We have only 2 options. How many are in favor of 4? 2. Not many taker. Rest are 8 or neutral. In between 4 and 8, there is no negative axis to cross. It's the 4 processor is going to be faster. 8 essentially is a hyper-threading. What you're doing, you have a physically one processor. Hyper-threading is virtually dividing it, making it 2 processor. When you do hyper-threading, it's a virtual arrangement internally. So obviously it is going to do that same processor only, but now you are overloading it. So it has to do the job and it will lose out time in that. So rather I would use the complete physical processor what I have in hand, doing that virtual things. So hyper-threading is a buzzword in that way, but when I come to computing, I mean, good for laptop, good for talking friends, corridors, college students. When I come to computing, serious computing, for me, it's a useless stuff. I would not like to do any hyper-threading. Essentially fooling me a lot. One physical processor, virtual, I said, okay, you divide it. What are you going to divide it? You are going to only use that physical processing units only. It's a chip. It has these cooling issues. It has its own processing issues. So that answers that online questions. Okay, so always the physical processor use is better than doing hyperthreading. So all these what we are talking, it's part of. You have any question? Yeah, that's the issue again, part of the parallelization. This is what I said, what we started off talking about. These issues are issues connected to the parallelization. Okay. You hold on to this. I'll come back to that slightly late, so that probably you might have your own answer to yourself, or we can discuss it later. So any other questions on the online? So anything else? So let's move to the parallelization part, which would allow me to do all this. So one of the important issue in parallelization is the concurrency. What is concurrency? You say that the definition, the property of the algorithm, which I said how precisely or accurately you do that a number of operations that you perform by separate processors at the same time. I probably gave you the example right now. So that's what it is. If you have a different architecture, they are going to lag because your concurrency is not going to be the same. So it's a key concept of designing your parallel algorithm. That means when I have a program in hand, when I'm trying to parallelize, this is very, very important how I parallelize it. I cannot do parallelizations arbitrarily. If you do it arbitrarily, it's going to kill it. Actually, it becomes a killer rather than savior. Okay. So you have to look at it a different way. How can you solve the problem? You require different approach, how you approach the problem. When you talk about the parallel algorithm, one of the very, very fundamental terminology is the scalability. So the scalability is that how I can scale it up with the number of processors. I think probably the question which Gokul has is the same. Can I push it to multiple processor if I have a job in hand arbitrarily? No, it's not going to be scalability. So scalability is another factor one has to keep in mind. Then obviously the speed up is connected with scalability. If it is not scalable, I'm not going to get the speed up. So this can be also associated with my architecture is not uniform, I'm not going to get the speed up. Obviously, scalability and speed up, they are little bit interconnected. That allows you to the execution time that you have. So obviously the typical way of defining the execution time is that how you compare with the same job, I do it in a serially and same job, I do it parallelly. So you try to see how, obviously you need to have an algorithm which would be highly scalable and giving you the speed up. Obviously what you would like to reduce is the parallelization overhead. That means you don't want to lose out communications, things like that. So those issues one has to take into effect. Now, that means if I have a particular problem in hand, and for example, let's say 1 million simple rectangular grid point, 2-dimensional that I would like to solve for problem, I can solve it in that 4 processor in i13. Now, same job, I can push it in the 8 processor in HPC environment. I can push it in the 16 processor, 12 processor, whatever processor. What do you think? If I increase the number of processor, is that going to be advantageous for me in terms of getting the solution in quick time? Or what is the guess? Let's say same job, I fix 1 million, go to 4 processor, 8 processor, 16 processor, 32 processor. So which one is be more effective? 32 processor, right? Huh? What do you think? Guess? And doesn't need to be answer is correct. Otherwise, we are not here. or I will not be getting my lunch today. What do you think? So somebody said 4, so his lunch is fixed, mine is taken care of. I mean, assuming if you are solving fluid flow problem, all this is where you have to use the brain, your understanding. 1 million is good enough for a 4 processor in a thumb rule. If I put it to 8, 16, 32, you would see the execution time would be more. The reason is that it's not the execution time, it's more you are halting the process to the inter process to communicate. It's the communication that you are going to lose out more time. In parallel algorithm, one of the key challenges is that how effectively you distribute the job amongst different processors so that you reduce your communication time, so that you do more. See, always we try to do more floating point flops rather than losing out time in communication. This is the ideal example where you lose out time in communication rather than doing flops. So flops is always preferred because your architecture supports that. So you need to exercise the resources that you have in your hand rather than doing it blindly. This is one common mistake. Even today, standing here, I can openly say that though it's recorded, my own PhD students making these common mistakes every day. Oh, I have 13 million, 15 million job, I'll push it into 500 processor. It's just going to kill the time. That 13, 14 million problem, probably 80, 64, 120 processor would be good enough. This is little iterative where there is no exactly thumb rule or formula which will tell you, because every problem is unique in that nature. Then what kind of physics you are solving? If you have a really nonlinear physics to be involved, multi-scale involved, then obviously you will have some, even the flops might take time. But typically, you lose out more time in communications if you just blindly push up to the more processor rather than thinking wisely and doing the things. Does that answer your question? So you have to switch your brain, make sure your parallel algorithm. So you have to understand how your parallel algorithm works. You might have developed, might have not developed using something. You need to understand. If you don't understand that component, then this can lead to an error. It's an example that you have to solve these typical problems here. How do we do this problem into the parallel system? I have the single, I can do it in single processor. I'll get some execution time. So I'll divide in 4 different segments. So once I divide that in 4 different segments, and why those numbers are always, we are coming back to the 4, 8, 16. Anybody has any guess? Why I'm not saying 12, 24, things like that. It depends on your architecture again. Typically, these are based on your bits calculation. So you need to understand what your processor is doing. What is the architecture you have? So if you try to divide the problem in that fashion, it would be faster. So obviously, you divide in 4 different domains, try to execute that, you are going to get it quickly. So there are typical problems, which is protein foldings, which involve large number of independent calculations. Independent calculations which do not depend on the data from other computer. That means I have distributed that for multiple computers. I'm doing independently here, I'm doing independently. They don't need to talk to each other. But typical fluid flow problem, they need to talk to each other. So those cases, they are kind of tagged as in, there is no independence in the intercommunications data. This is the embarrassingly parallel and they can be executed, which is probably the one which so these are very good problems or ideal problems for parallel algorithms, where you have a set of comments which are independent, set of comments which are independent, set of comments which are independent. Then if you spread it over multiple processor, you get the computation time is very quick. And these are ideal concurrency it will give you. It can give you highly scalable system. So each problem, as I said, are unique in nature. So unique strategy to handle it. So you need a way of doing the parallelization. This is where most of the nonlinear problems that we have they come under this category. Okay. So obviously you need to implement the things. So what you need is the flexibility to solve the problem in parallel paradigm or parallel setup. How I do that so that I get proper scaling of it. So obviously you have to do some kind of an things. So what you need to understand all aspect of these possible dependencies of the problem. For example, if you look at the pressure force, I mean just an example, which is locally concentrated, but when you look at the gravitational force, which is more like a global. So when you try to devise your parallel algorithm, you have to understand the physics behind it, the process that you are going to solve. What is the mathematical system you are solving or the physical system you are solving? Which component I can do parallelization and execute it, which component I cannot. If I try to forcefully do it, it's going to hit me back. So you have to understand that. That's what. So you always remember computation is fast, which we have already talked about. Floating point operation is much fast. Communication is always slow. So your parallel algorithm has to be very, very handy, creative. And another incredibly slower process is the IO, which we have not talked so far. That means when I take the data, writing that data in output format, because end of the day, output is something which I have to visualize. So this process is always slow. This depends on how your processor speed it, how you are trying to asking that particular, because I have a super computer sitting here or super master computer sitting here who is distributing the job to multiple computers, and this master computer has to do the writing. Now your parallel algorithm could be such that individual computer can write the individual domain, then you collect it. It all depends how your parallel algorithm is devised. Absolutely, it's a very unique characteristics. I can have a solver which will write this component, which will write this component, so that only at the end, even in the visualization stage, I can collate the data. I would not even come back here. This is where typical structural analysis case where you get into trouble, because finally the whole domain you need to back to this master node. You have to write it out or solve the problem. But fluid flow problems are handy in that fashion. I can segregate the writing IO part and IO component and can get faster output. So this is something, again, depends on your architecture. Architecture of what? What do you think? Which architecture is going to play a key role in doing your IOs? Except the algorithm part. I am talking about hardware. Which hardware of your computer is going to play a role? Huh? GPU. What is that? RAM. What else? GPU, RAM, cache memory. What else? Huh? Graphics. There is no business in graphics. It becomes colorful fluid dynamics. It is computational fluid dynamics. Storage. Something more to it? Add. Okay, all these are valid things. They are all going to affect cache, RAM. I would not say GPU, the master node which has the processing power. It could be GPU, CPU, that power also. Now again, little bit connected with my parallel IOs. I am going to write the output in parallel way or serial way. Top of that, which somebody said storage, but somebody didn't. None of you said one important component: hard disk. Speed of the hard disk, the storage device. That is also going to play a critical role. Typically, your desktop computers, you ask the vendor to supply, they supply. Do you know that they call it now these days you use SSD drives. Why they are preferred? Because the IO is much faster. SATA device, which are these days are obsolete, but SATA also can be powerful. You know, every hard disk has RPM. How many of you know that? 7K, 10K, higher than that. More and more RPM if you had, it will be faster IO. So when you buy computer, so try to do one thing. If you have a computer, go back and dismantle. Try to assemble yourself. You'll learn a lot. That's probably the best way to do things. Okay. I can give you this advice. 22 years back, I did the same thing. And then you know what can happen from parents. New computer came into my house, 2 days, I have dismantled everything. And I became totally clueless how to reconfigure it. But that probably taught me a lesson of how computer architecture worked 24 years back. Let me put it 1990, 2000, I think exactly 2000. But that teach you a lesson, how the architecture work, how they're connected. It's a very simple. Now today you get me the pieces, I can assemble computer like within half an hour. I just give you in writing, I can do that. You have to understand the components. What you are doing, if you are passionate about it, sometimes break it down. Break it, I mean, the failure teaches you the lot. Break it down means don't make it a situation you cannot reverse. So don't make make a reversible process. Don't make it the irreversible process. The entropy only increases. Then your house front entropy also will go up. Okay, don't do that. But what I'm trying to say is that you learn a lot. Okay. So this is something one has to also take into account. The other things in addition to concurrency, scalability, you have other issues which are there, though I'm not going to cover everything here, but I'll touch upon quickly so that you should have a fair amount of idea how this works. Locality, granularity, modularity, flexibility, load balancing. Load balancing is something which I said that, I mean, this is to do with that 1 million, pushing it to 4 processor, 8 processor, 12, 16 processor, like that. These are all these components which are components of your parallel algorithm. When you are writing parallel programming, you need to take care of all this. Okay, so typically the architecture, you have memory, you have control unit, you have logic unit, then input outputs. So all these are processing your set of instructions. So you have to see each unit is doing its job. Somebody is fetching data. That's what, when you say that the writing and all these things, why memory becomes important, why cache become important, because these are important things. Okay. Then arithmetic unit which perform the operation. Operation is always good because I can get very fast, but rest of the things, these are all interconnected. IOs, this is a very well-known architecture for now, like our body taxonomy, there is in parallel algorithm, they're called a Flint taxonomy. Different kind of situations possible. Primarily single instruction, single data, single instruction, multiple data, multiple instruction, single data, multiple instruction, multiple data. So SAID is that standard serial computer, what you do, single instructions, single data. Single instruction, multiple data. This is where you try to use in an image processing, graphical system, and kind of where you are pushing things to the GPU. GPU kind of understands the things in that process where you set the single instruction in multiple data, which is essentially mapping of the data structure. Then multiple instruction in single data. This is a single data stream which is operated by different sets of instructions. Okay. Typically, this is not very common or very handy for parallel algorithms. You don't do that. This is kind of discarded option. MNID is also very handy. Okay. Commonly used in the computer program. Each processor can execute its own part and finally get back the data. So this is how you try to devise the system. So then this little bit connected with that hyperthreading. I have memory. When I try to do hyperthreading, the same memory is going to be used by the virtually 8 processor. So it will slow down. So you could have shared memory. When I distributed over 80, 40 laptops, every component of the algorithm is executed in a laptop where that is using its own memory. That is handy because I'm not overburdening my master system. Or hybrid system you can do. I can use the benefit of that both. So one hand you could say that sometimes what happens is that, now I will come back to that, is that I have a job which I can put it in that one computer which has 4 processor, it has its memory. And I distribute the job. Job is, let's say, fairly reasonable event enough to do it in, carry out in 8 processor. I'll put it in 2 computers of 4 processor is. Okay. So obviously both the computers are using their own memory, things are faster. When I do that 8 processor and using through hyperthreading in one computer, that's sharing the same memory, it slows down the process. In hybrid architecture, you can sometimes, I mean, what happens is that where things can go wrong, your parallel algorithm, some solvers which is highly scalable, some solver which are not scalable. It depends how you are using the memory architecture also, because the RAM that you have. You can see some of the problems or programs. So, the large HPC system, if you go to those, I showed you the things. I mean, they are having individual computer. You can have even up to 80 processor, even more than that, 80 processor, single computer. Now, I can submit a job. Let's say job is big enough, 80 processor in that computer. It has its own memory. It will use that. And I try to submit that job to 160 processor. So the parallel program is such that it is not allowing me to distribute over inter computers, or there is a algorithm related issues. It will rather slow down. As I said, assuming the job is of big size, it is theoretically scalable over 160 processor. But when I push it, the parallel algorithm would not support that. So even though I'm trying to exercise the resource I have, I'm going to lose out, because the program is devised in such a way or designed such that it uses that local memory, which is the shared memory, because one computer has 80 processor but has one single memory, which is a shared memory system, which works faster. As soon as I try to distribute, it has to use shared as well as both the things, it doesn't work. So it's the issue of your parallel programming, how you devise your parallel algorithm. Actually, for the commercial package like that, it becomes to some extent black box for you, because you don't know how they have devised the pack. Unless you have worked sometime, or if you have a good friends in ANSI somewhere who can, the development team who can let you understand how the parallel algorithm works. Okay, but little bit I have understanding of the ANSYS. I can tell you, ANSYS program is just like a tree structure. Every extra solver kind of you see, it's just a main stem, it's a branches. That's what the UDF works in that fashion. You are plugging to a branch. It's a kind of a tree structure where the data structure works, or the whole solver works. That's what their development team in different module work in standalone quantity. They just plug in that into works, because it just try to use the framework of this main stem. But how the whole parallel algorithm works, unless you understand that, this will still remain a black box, and you hit and trial and try to see which one is more effective. You don't have an answer for that. At least I don't have. So what are the parallel programming modules that you can use? I mean, OpenMP is one kind of this. OpenMPI one can do. MPI, which has been old fashioned but still very, very effective today, which uses massive GPUs, which have their own things. Then this is the question which came up earlier. I said the processor and cores, how you kind of execute the things. So these are some of the interface that one has to use to define or design your parallel program. Okay, so you can use some of them, depends on, so how they are, which one I'm going to use. It depends on what architecture I'm going to exploit. So that means I need to understand the architecture a bit, then only I can exploit it better. Maybe my solver, I can push it to GPU, it will use the architecture effectively, I would get faster output. My program is not capable of doing GPUs, I should stick to CPU. If I try to forcefully push it to GPU, I would not get something effective. So things which are connected, as I said, embarrassingly parallel, master slave, threads and all these, then single program, multiple data. So, or other program implementation like GPUs and CUDA. So this already we have talked about, which is ideal for your HPC application where you do independent operations. So these are computer graphics, protein folding, geographical land, data mining. These are where like these are kind of under the umbrella of the embarrassingly parallel system, which are ideal for your HPC system. But fluid flow problems are slightly different. So what you do, you have a master node, which is sitting the top of like your instructor in a class, which always gives you instruction. So this guy is like that, who is the villain of the whole problem. So he sends information to these. These are called slave nodes. These are the terminology which are used in any parallel algorithm. So he sends the instruction, comments, or to the slave nodes. Slave nodes do their job. You get back that, and then finally call it here and get your IO out and finish your task. Multi-threading, which probably we have talked about, whether you use the course or you do hyper-threading to use it. Now, OpenMP allows you to do that. So when you do the hyper-threading, you should have the supporting parallel algorithm also in place. If you exercise that hyper-threading, probably you get the good output out of that. If you don't exercise that, only just using the hyper-threading thing in the sitting in your computer and try to submit the job, it's not going to give you the ideal output that you expect out of that. Okay, so this typically OpenMP allows. So that means you are under the shared memory system. I have a one shared memory, I'm that pushing it to multiple processor. MPI system, it just master node. You send commands to all slave nodes, collect back the information in the master node, try to do that, and that is done through the message passing interface. So there is a set of comments. So let's say I have to do x plus y equals 2, 2 plus y equals to 2. So like the example I said, the master node wants to do the x square plus y square equals to something. He needs x and y in the complete domain. The master node has divided that. That is called the load balancing. Send the instruction to the slave nodes. Slave nodes would solve x plus y equals to 2 and y minus x equals to 4. Get back the x and y information for individual domain. Then master node will do the x square plus y square. He needs back this. And this is what your MPI would allow you to get back. If you want to do this processor, this operation at the same time, you have to wait for each of these slave node to send you back the data. So you would not continue with your operation x square plus y square unless you get back from everybody. So somebody will do at faster rate, somebody will do at slower rate. You have to put some MPI command here to stall it, so that you make sure at that stage you get back at the same time. You have all x and y, do the x square plus y square. Problem definition could be such that I don't have to depend, I can still go ahead. Let's say that x square plus y square, if I do it in the slave nodes, I don't have to have that bother. I can continue doing that and writing my IOs. But at the end, when I have to finish my job, that time everybody has to stop at the same time. Otherwise, I'll corrupt my data. So it depends at which stage what you would like to have. Now, this is what a single program execute all tasks simultaneously. This is single SMPD, and then multiple program do the multiple tasks. That means you have all A dot out, B dot out, C dot out in different tasks. And so different example problem, they communicate in a different way. So this is also depends on how your program is going to work and how you design your algorithm. Then GPU, which is now the high-end architecture that you have. So you try to use the cores of the GPU, but you have to write your program in GPU architecture based supporting algorithms so that you exercise the GPU. Okay, obviously, it's not always necessary that the complete portion or the part of the program could be put to the GPU. So what is important here is that when you try to design a parallel algorithm, you need to identify the bottlenecks, hotspots, essentially which section or segment I can do parallelization, which segment I cannot do parallelization, which will give me trouble, or what kind of instruction that I'm going to or I'm trying to parallelize. So all this, your understanding is very, very important before you do any parallelization. Then after having that understanding or comprehension, if you try to do that, then you can exercise the resources that you have in more effective manner. Otherwise, you will get some parallel things going on, but it may not be effective. But as I said, parallelization, one more important is that not the floating point operation, which are the killer. It's the killer is the IOs and the communication. So your algorithm should be such that you try to minimize those as best possible way, depending on your physical problem that you're solving. Okay. So is any question there, or shall I? So now I'll get to that thing, the OpenFOAM things. So this should continue even in your first hands-on session. So I'll just quickly showcase the OpenFOAM some fundamental things. So now today's date, as of today, OpenFOAM, we have two different versions. One coming for .com ESI version, another is .org. Till 2015, early 16, they were together. Then whatever happened at the household level, you never know. They got divorced. Since then, they are having their two development things. Today, .org following since then 5, 6, 7, 8, 9, 10, I think 11 has come. These guys are following with the year-wise version, 1706, 1702. So they release two versions every year. Now, right now we had latest 2312. So fairly the problem, tutorial problems, basic structure, everything is same. Obviously, both of them have added some features to it. Now, if I talk about today, if I have a solver which is working here, can I take it there straight away? The answer is no. But by and large, 80%, 90% would be similar. But that 10% you have to put an extra effort to make sure you make it compatible with that. Similar, the reverse process is true. So the challenge here, whoever is going to use OpenFOAM or OpenFOAM users, keeping updated with the version is a big challenge. Otherwise, every year, if you see, they release one version, they release two versions. So keeping your code with the new version updated is a different challenge. Obviously, if you are using the default modules, then you don't have any challenge. You are a happy person in the world. So anything comes up, you can use it. But the thing is that today, the major difference coming in from the way they have defined their data structure. Since 7 or 8 onwards, this guy changed the data structure totally. Earlier that even the codes were compatible with some changes in the vector definition, things like that. But now it is very, very difficult. So my earlier statement of 80-90% now has come down to 60%. From here, the solver, if you try to here or here to here, probably 50 to 60% would be compatible, the rest is not. The reason is that both of them change their data structure from the top level, because all these solvers, important thing is the data structure, how you handle your arrays, the definition of the data structure. And these are based on C++. So the class definition, public, private. So they have changed it intentionally so that this doesn't compatible there. So but this is the status as of today. So you have to be a little bit careful which version you would like to use. But the tutorials and all this we'll do whatever version available in the HPC, but that would not stop you going to use in the other version. Fundamentals remain same. So obviously, can you use it in your local computer? Yes, there are pre-installed version in Ubuntu. I think now both of the versions giving, I might be wrong, Windows executable, but how effective they are, I don't know, but you can always explore because Mac, Linux, everywhere it works. Windows also. How effective, as I said, I don't know. So you can follow the installation in the site, and you can download. So this when from 9, I just picked it up. So you can do that. And once you do that, you get these pre-installed packages. These are the structure. Probably in the next session, hands-on session, you would be made familiar to all the structures, so that before you go to the afternoon session, so you will get all these data. I mean the directory structures. So they will have applications, beans, doc, and all these. They're having their own configuration. I would have some of them here. So this, if you blindly pre-install the package. So there are some users where user guides, discussion forum, you can actually discuss things, some problems they have included. So, I mean, today you have a lot of tutorials, a lot of other materials are, I mean, I would say abundantly available in the internet. But yes, I mean, this is again the source code from 2112 where you get to see this even the browser you can open. These are the source code. You can get to .c files. You can see it. You not necessarily have to install things. Even the browser, both the version, you can go and have access to the source code. You can see what has been implemented. So basically the mathematical formulations can be visible. So one can explore that. So how your problem has been converted to the program. There are plenty of literatures and all these, but this is a key message. Very easy to get frustrated with OpenFOAM. And I would not be surprised if you are trying to do it first time. But don't give up. If you struggle, you'll learn a lot, but probably someday you'll see the light of the day. But yes, I would not deny that the learning curve for OpenFOAM is little stiffer compared to using a commercial package where you have a nice GUI-based architecture. You can click your buttons, get the results out. But here you have to actually get into the code, try to do things. Basically, I would say that there is not much difference between an experimentalist or a user who is going to use OpenFOAM. You have to get your hands dirty, period. So it has plenty of capabilities. It's a open, but under GNU license. You can do your development, push it back to the repository. You can do that. You might have done some development. If you want public to use it, you can do that. If you don't want, you can stop it. It has different kind of solver capabilities, CFD, heat transfer, multi-phase reactions. I mean, all these you can see even in the internet. It's not something I have invented. So all these are capabilities. As soon as you go to that site, if you see what are the solvers is available, it will give you the list and the table. It has these libraries. These are the important libraries that you need to fetch for solving the different terminologies. You have all these are based on finite volume approach. You have many pre-processing, post-processing tools are there. You can send the geometric information grid from outside, like I can use ANSYS or ICM CFD, point-wise, any other software, third-party software, generate my grid and push it to this. Obviously, the solver you can do, there are a variety of solvers which are available. I mean, this has a lot of capabilities which in hand. Obviously, the first line is the important discouraging line. There is no GUI. So you have to look at in the, so which means you also have to learn some Linux commands. Even sitting in a Windows terminal, you can connect to your machines, but these things work better in a Linux environment. So you need to understand Linux, you need to have Linux commands, and probably we'll do some of this exercise in the hands-on, first hands-on. First hands-on is kept for that only, so that you get familiar with these things. So it's written in an object-oriented, as I said, C++ fashion, so class structure and all these things, but obviously all the source code available. Let's say one can develop a new solver, which is quite easier, because let's say I have to develop a solver like this, and the instruction is this much. So, but this instruction this much, but I need to understand what DDT does, what divergence does. These are the syntax of the OpenFOAM. So DDT means time integration. Divergence means it's doing delta dot something, this operation. Laplacian means it's doing delta 2. So source term, if you don't have 0, there is a source term. So you need to understand those syntax. Then this looks like a toy. You can play around it like anything. Okay. So when you look at the directory organizations, anyway, these are going to be again covered in your session. Initially, you can see I have shown you some graphical things. It will have applications, bin, doc, etc. Every directory will have a different information. So then if you go to the application and utilities, you get to see these things, which are means, sorry. So which means that you have this different directory which includes some of the basic information. Combustion includes some of the basic combustion. Multiphase includes some of the multiphase information. So this will also, so as soon as you get your installation or once you log into the system that you have you can go and see what are those. Okay, probably there is a document that TA is going to also share with you. And then in that particular session, try to get familiar with all this. Okay, so all this, I mean, exactly my portion of the slides only PDF he is going to share with you, so that I don't want to spend too much of time. Then here you can go to solvers. Inside that you can get different kind of solvers. Every solver does different things. And what solver does what? You can again go to the internet version and see what are the solvers that will give you information. Okay, icophone is a pure incompressible steady state solver. Probably pimple foam or piezo foam is an unsteady solver in incompressible. So when you say incompressible, compressible, the way they are different. You have all these solvers which are sitting there inside that, and different kind of solver directories under the application utilities. Okay. Then yes, you have to explore the source code. That is what the purpose of the first handout session, that you explore all these things. Then you come to the complete environmental variable. You get to see all these. Then you can go to the aliases. You face the tutorials. Here you can go to the tutorials. You can see based on different directory structure there, incompressible, compressible, multiphase, reaction. That means under that you will have a 1 or 2, 4 different problems which are the tutorial. You can blindly run that. They have the setup. If you blindly run that, there is a README file which tells you, okay, this is how you can run that. So always the master structure would look like that. Then you can, so these are the thing, if you hit command, then it will send you back which directory you are sitting in and how it looks like. If you go to application, it will have solver, test, utilities. Utilities means once run is done, then what are the basic utilities that is available that I can use to post process my data. If you go to bin directory, you can see these are all bin files or executable files during. So you have all essentially what you have all the source code in terms of .c file. When you compile it, the .c made the .o files. And then make a bin files which are sitting there. Okay. And then they are made the linking. And finally, you get the solvers which are executable like your a.out. But they are given name that essentially they are a.outs. So the etc structure will have all these directory structure. These directory structure something connected with your problem running directory. Sometimes this is connected with your solver development directory. So for example, the thermodata, that particular directory is usually does the thermodynamic calculations. I have typically used the property of the thermodynamic property of the system, then you do the calculation. So those directory does those calculations. If you go inside the directory, that directory you will see finally, probably you have obtained the CP, CV from there, you calculate internal energy, enthalpy like that. So those are the thermodynamics property. End of the day, you have to do those calculations. So it was done in different fashion. It's distributed over so that every different solver can face that information. As soon as it will call the thermodynamic data or include that structure, that operation would be included in that your operation. Okay. So you can then in the platform under that where you have these applications and source file, and then whatever the architecture that you have compiled, it will create the another version of it, and all the executables will be sitting there. And then in the SRC, you will have all these different options, finite volume, Lagrangians, combustions, and all these are there. You can, I mean, you explore that during the session. This is the SRC structure continued. Then in the tutorial, if you go, as I said, you will say they are segregated like that. Basic tutorial, combustion, compressible. If you go combustion, that means it will have the reacting tutorial. You go to electromagnetics, DNS, financial, different tutorials are given. So it has been also given an instruction how you can run those tutorials. Blindly you can do that, but you explore. So that means when you say that I want to use a basic, probably it's going to use the typical incompressible ICOFOAM solver. If you try to go multi-phase, it might be fetching the solver which is there in the under the directory application in the solver. So solver compilation .c files are sitting in SRC. Executables are made in the under solver applications. My tutorial directory is having different kind of tutorials, which, I mean, there's a whole range of tutorials available today. I mean, you can define your problems from there. Then how you can compile things, wmake commands. Then this is your user directory where you want to work. Okay. And then you can create your own user directory, fetch something from there, copy it, and then try to modify it, and then add to the system. This is a source code, how you can fetch through some of the Linux command. As I said, this file would be shared with you so that you can go through step by step, practice that in the, see, looking at the slide here, this would not give you the flavor. Once you have the document, you try to explore in the thing, then you would be able to see it. So these are another structure you can extract out. Environmental variable, how you source it, probably that's the first bottleneck you will face it. As soon as you log in, even you try to do first comment, do anything else, just don't wait for the TAs. Login, user ID passwords has been given to you. You just type which space ICOFOAM. You see that what error it gives you. Probably that's the best starting point that the TAs will start up. Everything is installed. It's not showcase that solver. ICOFOAM is the basic incompressible solver. It's not going to fetch it, but though everything is there, just do that. That's the first command you type. That's out of curiosity. You see the error. This is what you have to work on the bash or say first thing. This has to do more than OpenFOAM is the Linux. This is applicable to, if I have to face today the Intel compiler, I have to include it here. It's the environment of the Linux system. It's called environmental variables. The general solver, you will have, as I said, the .c files that once you compile it makes the bin file, and then finally the executables are prepared. Okay. And you can go to different solver directory. You will be finding the make command, which is the set of instruction to compile these .c files. .c file is exactly doing the mathematical calculation that you want to do. A plus B equals to C or C plus D equals to B. That is what is implemented in that .c file. These are some of the utility. This is the application utility. So you can see the directory contents and always can fetch the help through these commands. Okay, these I have already talked about. These are some of the commands that you have. Yeah, as I said, the ICOFOAM, it has to be no space. Syntax is very sensitive, so it has to be all lowercase ICO, F capital form. Unless you type it separately, it will give you different error. So just type this which space ICOFOAM after login. You see the problem. Okay, these are all different solvers. We would explore few of them. You can see how they are. So essentially, you have to take your time, explore the source code, how the directory structure look like, how the environmental system or the variables looks like. Now, when you go to the case setup, which would be again done in the afternoon, typically the case setup will have these folders: zero folder, system folders, constant folders. I would just explain a little bit. The constant folders will have a mesh information. which can be given from the outside, or you can use the internal utility to have this mesh, which will have the number of points, phase, connectivity, and all these transport properties. That means if you're solving a fluid dynamic problem, you know which are transport properties you need. You need viscosity, diffusivity, thermal conductivity, all these are transport properties. Those information should be there. Then the system file, there would be three different text file: control dict, schemes, solution. Control dict is the set of your instruction, how you would like to run through that operation, all basically control operations of the execution. Schemes are the things, how your numerical scheme is going to behave, whether order of accuracy, second order, first order, things like that. So that is you can control through this. So the way this has been done, that once I have different kind of schemes again inside the solver available, which one I would like to use, I can control from the schemes. Then the solution pattern is how am I going to solve my linear systems. So those informations are given. I have these variable like flow variables in terms of U, V, P, if I have temperature and other things. So this is how typically the directory structure of the case file, what it looks like. Okay. So I think if you have any more questions, I would be happy to just take it up now before your break, and then the follow up with the first exploratory session. Any doubt, any questions or anything? So three key things that we have discussed here. Obviously, most of you, or almost 99% of you, has background of CFD, but anyway, CFD basic structure, where the numerical methods become important for a CFD solver. Then the important aspect of the HPC, where the architecture, how the HPC system works, what is the progress and all this. That leads to the HPC. When you talk about, essentially we were talking about the architecture part, hardware, going to the parallelizations, which is essentially again software issue, but utilizing the hardware architecture that you have, making your CFD code to be effective. And then finally we're coming down to what this OpenFOAM is all about, how it looks like. And then this session, hands-on session, you would explore those things. Okay. And then the afternoon session, once you are done with this, we'll start with the incompressible solver, how this has been implemented in OpenFOAM, and then follow up with the hands-on on the incompressible solver. That would be end of the day. Tomorrow we'll do the compressible, hands-on, go to multiphase and turbulence modeling. Everything will be followed by the hands-on. So the idea there is that to showcase, we are not going to teach you basic CFD here. How the code in OpenFOAM essentially implemented, what are the syntax, so that you can correlate that. Okay. Is there any question or anything? Online forum? The question here is that can we run these codes in Windows? Probably yes, but I'm not sure because in my lifetime I have never tried it. So I cannot give you the exact answer. Probably yes. Since they are giving you executable, probably yes. But as I have not tried, I cannot 100% confidently say that yes. I have been using, or my group or students, they are using in the Linux environment only. But these things we never, I would say is a, we would dare enough to go to Windows to do these operations. Windows is layman's operating system. Here we are talking about serious computing. Any other questions? Okay, thank you. We'll then break for half an hour. Around 12, we'll be back for both online and offline. I mean, all our participants for the session, hands-on session. Thank you.
The voice is not audible.
Sir, your voice is not audible.
Can you please go through the steps once again?
Sir, your voice is not audible, sir.
Sir, please go through the steps again. I missed it. So voice was not audible.
Am I audible now for the online participants?
Yes, sir.
Okay, thank you.
So no
So-
one has got the test user accounts here, right? No one has got. Can from the online participants, can anyone confirm if they have got the test user accounts? Please
Yes, sir, we got.
ping it in the Teams chat. Okay, okay. So is it visible from here? Okay. So just okay. Uh,
Sir, I missed the session due to voice was not audible. This.
is it visible? Okay. So do one thing. Those who are sitting in the first two columns, take test user one. Okay. So there are 5 basically. So we don't want to overload a particular account. So do one thing. There are 1, 2. So first to take test user one. Okay. So your user. So Anurag,
Sorry.
just show the POMAX ones. the SSH part. User session and SSH. Yeah. So those who are using Mobax term, so your username, your remote host will basically be paramshakti.iitkgp.ac.in.
Sir, can I use the Ubuntu?
P is small over there, so that is case sensitive, I guess.
All right. So your remote host will be paramshakti.iitkgp.ac.in. Your username will be test user 1, 2, 3, 4, 5. So the last row, these last columns use 5. First two use 1, 3, 4, 5. Okay. Don't overload, because if everyone goes to the same account, you will not be getting the enough resources. All right. So how to access? So you can access it via Mobax. Okay. So just Mobax term, Google this, and you will get the software. Download it. You can use then by how Anurag is showing. You can use it like that. If you can use it by using terminal. So the terminal part is, go to your Windows option, click terminal. The terminal file will open. Okay. So the command for that is SSH -P4422. Then this paramshakti.iitkgp.ac.in, and in front of this, write your username. All right. As Anurag is showing, just write that in your terminal. If you don't have Mobax, so you can use Mobax term. You can use terminal, putty. All right. So these first two columns use test user 1, 2, 3, 4, 5. All right. If anyone is able to log in, please raise your hands. Log in, right? That side. Okay. Question. You can download Mobax. You can do terminal, whatever it is.
Yes, sir.
Portable edition.
You can use any of those. Yeah.
For downloading,
Download it.
Mobax term.
And then just click the next button whenever there is a prompt.
So password is basically test, then the number, then yeah. So test 2, test 3, test 4, test 5, exclamation mark 2, 3. All right. If you want to download Mobax, download Mobax. The advantage of Mobax will be you can download all the files, upload all the files that are required. All right. For terminal, you don't have to download anything. You can just download. Yeah. So go to, so your remote host will be paramshakti.iit.kgp.ac.in. Yeah. Do that. After that. Okay. Specify username. Click that box. Tick that box. Specify username. After clicking that box, write the username here. Write the username here.
Sir, like if we log in by test user to, the password is same, right?
It's low here.
If we log.
Okay, then you can use, so if anyone is having issues with downloading Mobax, use the terminal.
Hello.
And for the outside participants, they need to use
See,
the port
Mobax,
422.
Mobax is just, we have to download and upload some files. So Mobax is relatively easier. For terminal, you have to write the command yourself. That's the difference. Okay. So those who have terminal, please open the terminal. And Anurag, can you please just show the command terminal? Those who are having a slow connection, internet net speed, and having issues with downloading MOBAX, just see the terminal option here. Do SSH, whatever is written here, instead of test user 1, write test user 2, 3, 4, 5, whichever is your test user. Then just click.
Network error. I am getting a network error in MOBA XTEM.
Just log in into terminal and show once.
So you will get a captcha after you hit enter.
Yeah.
So please be careful while you put the captcha. It is very case sensitive and it can be quite confusing as well.
So the password will be test 1, 2, 3, 4, 5. It will depend, then exclamation 2, 3. Depends on whatever your number is, test user account number is.
How many of you are able to install and then come
Yeah.
to this screen as well, at least?
So when you have come to this structure captcha, please type the captcha and the captcha will not be visible. So you will not be able to see what you are typing. Okay. So write it, type it carefully. And after that, you enter. Anurag, can you just write and enter once? Okay, sorry, the captcha you can see here actually. The password you are not able to see. So you can see he has logged in to his test user 1 account. So this is what you will be seeing after you log in. So password is, I'm repeating, the password will be for test user 1, it is test 1. For 2, it will be test 2, 3, 4, 5.
And rest of the string remains the same, factorial 2, 3.
Sir, I have joined online. I am not able to download MOBAX. Hello.
Hello.
Haan,
Same
I'm
here.
not
I
Anyone
am
able
able
not
to
able.
access the cluster?
No. We are
No
getting
one.
a network issue. Network issue
Please
in
put your
MOBA
hands up
XTEM.
those who are able to access the cluster.
Some have already done over here.
Okay. Those who are still stuck in downloading MOBAX.
No network issue
Please
in
use
MOBA
command
XTEM.
prompt.
If you're stuck in downloading MOBAX, go to command prompt terminal.
No, the problem
Where?
is network issue in MOBA XTEM.
Okay. So the username is test user 1. Host name is IIT. I think you swapped the thing.
Where we have to
I
put
think
this
swap
username?
the test code.
Hello.
Can I have the marker, please? Marker.
Hello.
For people who are using command prompt, the command to enter or log in into the cluster is SSH -P, it is capital, 4422. Test user, let's say I'm using test user 1. So @ Param Shakti.
Network connection.
.ac.in. P is small. Yeah, this is all white spaces.
So it's a net.
This is for command prompt, CMD. Don't put this bracket, this is for separation.
So some might be having network issues and it will be showing remote that connection is closed, something like that. So those who are like KGP students here, you can you go to other societies also, campus secured, academic secured, and all the others.
Hello, sir.
How many of you logged in? Sorry? Error. Okay.
Sir, can you show how to use PUTTY?
Okay. If most of the students are not getting -4422, they can use 22 also if they are in the.
Okay, so those who are here in KGP, you can use, don't have to mention -P4422. Those who are accessing guest secured, campus secured, academic secured, no need of putting -P4422. -P4422 is for those who are outside campus. All right. So just cancel and for participants inside campus, we are using campus. Just can you do once?
Those who are physically present over here,
Delete this.
they can omit this
Muba-
particular flag 4422. They can use this and then try to log in if they are able to do it.
Mobile
Let me know if you are able to do it.
Hello, hello. Mobile XTEM cannot be used from outside. Hello, am I audible? Hello.
So those who are inside campus accessing campus networks, no need of writing port -P4422. Just do SSH test user name @paramshakti.iitkgp.ac.in. Anyone still not able to access cluster? Please raise your hands so you can.
Huh? Time like it. Shall we move forward if everybody is able to log in?
No, no, no. What we have to put the in command prompt to get the access?
Okay, please raise your hands. Those are not able to access the cluster. From here, everyone is able to access the cluster from this side. If anyone is not well, please raise your hands, or you will be lagging behind after this.
He is not able to do it.
Okay, I'm coming. Just saying.
Password is test. Let's say if I'm using test user 1, it is test 1. If I'm using test user 2, it would be test 2. Similarly, for other accounts as well. And it is after that factorial 2, 3. This string remains constant. Only thing is if you change the account, you change the string. Be careful
so
while you type the password because it is not visible while you type it.
Okay, from here, those who are not able to access the cluster. Everyone is able to access. Yeah, that is. Yeah. Everyone is able to access here. From the last rows, columns,
Sorry?
everyone is able. Okay.
No, you have to type this captcha. Whatever is written over there, you have to type it very carefully. It is case sensitive. And after that, it will ask for password prompt. Then you enter that password. Then you will hopefully be able to log in.
Hello, sir. Hello.
Okay, I'll show through mobile. When you open mobile XTEM, the screen would typically look like this. So you go to sessions, then click on SSH, and then type the remote host, that is paramshakti.iitkgp.ac.in.
Shakti.
Please type the name very carefully and then click on username and specify the user ID, that is test user 1. And if you are from outside campus, then type the port 4422. And if you are from inside the campus, then no need to change the port. It is by default 22, and then hit enter. Here password was already saved, so it will first, it is showing the error. Otherwise you will simply get a first captcha like this. And then you need to type it very carefully, similarly like we have done for the command prompt. So it is US. Then after that, it will ask for the password. To type the password, which is shown on the board over there. I hope it is visible for the online participants as well. So hopefully it will look something like this. So basically now,
Hello?
if you type
Hello?
PWD,
Hello?
you are basically in the home of test user 1.
Hello, sir.
If you are, user
This
test,
is
if
giving
you
a
are using
network
test user 2,
network
it would
issue.
be home test user 2.
No, this is giving network issue from outside.
So we'll first start exploring what is inside OpenFOAM. I'll come to the installation aspects later. I'll share one PDF. If you follow that process step by step, it will be accessible to all. You can do that. If you go to inside OpenFOAM,
Anyone still not able to access the cluster?
I'm not able to access by Movatam. Hello? Am I audible?
okay.
Hello,
So
sir.
anyways, don't worry about that. I will just giving this file for the demonstration purpose. I will provide it later. I'm not doing anything fancy right now. I'm not running any code. This for demonstration only, right?
No, no. Can you explain one more time that MOBA term, because I'm not able to access.
Which account are you using? So it is test 2, then factorial, then 2, 3.
I'm using test 1.
This portion remains the same. Only thing is this one change.
Hello?
Everybody has accessed the cluster, right? So we can proceed forward now.
Okay. So it seems that I have failed to copy the OpenFOAM folder in test user 5. So nothing to worry about. So some of the folders are missing. So nothing to worry about. I am just demonstrating the process. If you need those files, I will provide you separately on a Google Drive link. You can try it on your own. So basically, if you download an OpenFOAM tar files, I'll tell them later. So typically an OpenFOAM installation, if you go outside, I've already extracted the content of this OpenFOAM v1912. So if you extract, that command is simply, I'll not do it over here. It will take certain amount of time, like 15-20 minutes. So after the command to do this is star minus xvzf and then type the particular file over here. So it will, what it will do is, it will make a folder named as OpenFOAM. And for entering into the command, for entering into the folder, the command to do is cd OpenFOAM. cd is change directory. So if you do ls, ls will list out all the content inside that particular folder, right? So basically it contains, initially it will contain OpenFOAM v1912 and third party v1912. So for installing OpenFOAM, you first need to build certain dependencies. Let's say if you want to, first of all, you need the GCC compiler. First, you need a GCC compiler. And for that, there is make command. Before that, you first need to set the bash RC also. So if you go back, okay. I am just now at home. So this folder is basically at home. Don't go to scratch right now unless and otherwise stated. Those who are able to see the test user one, it is for them. This is the current directory that I'm working on. So PWD is the current directory. I hope if somebody is not able to follow, please let me know by raising the hand.
If somebody is not able to follow the commands, please just raise your hand. Okay, because you will be stuck after this. When the lab sessions will be going on, you will get stuck actually. Okay, let me just repeat what he said.
Hello,
So
sir.
after you have all access to your cluster, you will be getting some information about your accounts and everything. Then in the prompt, you will be seeing test user 1, 2, 3, 4. Then something is written. Okay. Then if you do PWD, just everybody do PWD once. Everybody do write PWD in your command prompt. See if you're in home or scratch. Just see what Anurag is doing. If you are in home or scratch, just check that. Then he's referring to a tar file. Just do ls once. So it froze, right? So just see, so he's referring to a tar file. Just do ls, okay? And we are able to see the tar file except in test user 5 maybe, right?
5 and 2.
Hello, sir. In 5 and 2, you might not be able to see this, which we will copy this file to in your test user account after this. So others must be able to see this tar file. So all the data and files that are required for your simulations are present in this tar file. So Anurag is showing how to unzip or untar that file. So just.
So the command for that is tar xvf OpenFOAM. Just type the tar file name.
Okay, so you just type this line. So untar that file or unzip that file basically. All right.
Yeah.
So you can do it now or you can do it later on.
It is advisable to do it later on because it will consume another 15-20 minutes.
Yeah.
So it's a very.
So just write down the command for untarring the file. This contains all the files and folders that will be later needed for you. All right. And it is in your home directory except for test user 2 and 5. We'll be copying that to your directory soon after this. Okay, so those who don't have the tar file, no need to worry. We will just copy it to your accounts. All right. And just
exactly type the name which is shown over there. Linux is case sensitive. So don't make mistake in that. O is capital, yeah.
Yeah. Okay, Anurag, I think it is test user 3, 4 also don't have the file. So
okay,
it may be in the scratch file, scratch or home. Okay, whatever it is. So we will just copy it. We'll copy all the tar file to all the test users. All right. Just write down the command to untar it, unzip it. All right. So you will be needing the
Should
command
should
to
we work
unzip it,
from the
and you will be
scratch
getting all the
or
files and folders needed to run your codes. Okay. So those who are not able to see the tar file in your home directory as of now, don't worry, we will be copying it to it.
hello? Should we run from scratch or home?
So after doing this, you must get a folder which is named as OpenFOAM over here. I've already selected it. So to go inside that particular folder, you need cd command and then press OpenFOAM, type OpenFOAM, right? And hit enter. So automatically the latest directory, it will be shown over here. You are now inside OpenFOAM.
Hello, sir. Hello,
Right.
sir. I'm audible. Hello.
This is basic
Hello.
Linux command that must be familiar with.
Hello, sir.
Again, do ls and you will see
No,
all
after
the
this, after
contents
executing the
of
tar
OpenFOAM
command,
v1912.
after
Primarily,
executing, hello.
OpenFOAM v1912 and third party v1912 comes by default. You need to manually configure it, compile the code, and then source the OpenFOAM environment. Then only you can basically fire all the commands of the OpenFOAM environment. So that is very long, hectic process. I'll just give a brief idea on how to basically compile OpenFOAM. There are certain tutorials online available. You can always refer to that. I have already shared one link. You can
Cannot.
install OpenFOAM in Windows
Are you
subsystem for
are you
Linux and then
no no are you
follow
able
the
to
same
hear
process
us?
that I'm doing over here.
No, are you able to hear us?
So inside third party, if you see, it can be a bit overwhelming. Go inside third party by doing cd third party, right? So if you move inside, you need first GCC compiler. GCC compiler, Intel compiler, you can use anything, but I prefer GCC for now. And also there is certain bit of dependencies for 1912, you need GCC 7.5 and higher. So GCC 7.2 work for me. So GCC 7.2, 7.5, 8, you can install anything. Stable version is GCC 7.2 for OpenFOAM v1912. But before that, if you move outside, if you go inside the OpenFOAM directory,
Hello, sir.
okay.
Hello,
So
sir.
inside OpenFOAM,
Hello,
there is
sir.
one folder named
Hello, sir.
etc.
Sir.
And inside etc, there is a file named bashrc. And let me tell you, these all green colored are the files. These are text files. So for opening those text files, you can either use any native editor software like gedit, Nano, VI, Vim. I use VI for my convenience. It is pretty much straightforward. You just need to type VI and then hit bashrc and then click enter. So inside this contains a lot of information. Before installing, the thing that I was telling you earlier, you need to set the GCC version over here. So it was GCC 7.2. So allowable GCCs are GCC 7.1 to 4. So you can put the flag GCC 7.2. It will try to fetch GCC 7.2 in the third party. Then again, another important entry is MPI-CH. So for parallel processing, you need MPI commands. And for that, you need separate package to be installed along with the OpenFOAM. So typically there are OpenMPI and MPI-CH available. OpenMPI is pretty much straightforward to install, or you can use the by default MPI-CH that is already available with you. I'm not aware if your Linux system has already pre-installed MPI packages. If it has pre-installed MPI packages available. You just need to change the flag to system open MPI. So it will try to fetch the MPI packages, and then your job is little bit reduced. So this is a typical bash RC file in the OpenFOAM directory. So again, what I'm doing is I'm going inside third party v1912 directory. I've already set all those flags in the bash RC. Then there are certain all wmake commands. Make GCC, make CJL, all those are dependencies that you need to install it beforehand. So in order to use OpenFOAM, I've already done this whole process before. It is not possible to show it right now because it is a 6 hours or 7 hours long process. What I am going to do is I will be using the native installed OpenFOAM that is available to everyone. You just have to source it in the directory. So moving on further, I will basically tell you about SRC directory. So if you move inside OpenFOAM, my present working directory is this, please note that. And inside OpenFOAM, there is SRC folder. So this is the whole crux of the OpenFOAM where all the codes are implemented. Let's say if you want to look on the turbulence model, you can go into that folder. Let's say if I go inside the folder, there is whole lot of, again, compressible, incompressible kind of formulation. For multi-phase flow, there is another turbulence modeling that we need. So all these things are segregated. There is certain standard turbulence model also available inside this, such as RANS-based turbulence model, K omega, KSST. Don't worry for now, I'm just giving you the case directory. Uh, uh, for working you in the future, you can always look into that particular directories according to your convenience. So RANS-based turbulence model are available in this RAS folder, RAS. So over here, you must have come across various kind of models, K omega SST, K omega, K epsilon. All those models are already implemented over here. So what we do during installation is we fetch all these codes, give it to GCC, make the executable, and then we can say that OpenFOAM is already installed. It will, whenever we next time fetch the code, it will look for all those executable and then use it accordingly. So our headache is gone. We don't need to code it from beforehand. We are just reusing the codes that is already available in OpenFOAM package. So this is all the implementation that is available just in turbulence model. You can again go back. For going back, let me tell you the command for going back one step directory upward is cd dot dot. If you want to go multiple step at a time, cd dot dot slash dot dot slash, but you need to have a bit of grip on the directory at where you are. So always before what I do is before going back, I do ls. I see at what directory I am, or you do pwd. So I am at the SRC. If I want to go one step back, let's say there is something else to be done at one step back, I always do cd and then again do ls. So it is a bit more convenient to visualize at what position you are in. So in SRC, again, there is a lot of libraries that are available that can be fetched at runtime of the solver. So this is one of the aspect of OpenFOAM. Then next, all the solvers are there in the application directory. Just giving them the idea. Yeah, that it's only available in test user one. It will be provided later during the session. Okay, so what I was talking about is all the solvers. Let's say in CFD, you might have learned about simple algorithm. That is the first starting point of learning CFD. So all the, let's say if I want to access the simple algorithm, inside this, we have solvers. In application, we have solvers. Again, if I do PWD, I am basically inside application, and inside that I am inside the solver. And again, if you do LS, there are certain again folders available based on the application. Let's say if you want to solve heat transfer problem, all the solvers are available in the heat transfer directory. If you want to do incompressible kind of simulation, let's say a flow over a cylinder or something like that. So go inside incompressible. And what sir was talking about earlier is icofoam, simple foam, pimple foam. All those algorithms are already coded inside here. We can customize according to our need. Let's say if you want to customize the simple foam algorithm. So inside simple foam algorithm, there is always a .c file and create fields.h. And these are the equations that we need to solve, right? So if you open simple foam.c, it fetches all the .h files that have been dynamically linked. I will explain you in the due course of time. What it does is it solves the pressure velocity coupling problem by solving first the momentum transport equation, which is coded in u equation.h. So this is basically momentum equation that is being solved. This is the divergence term that appears in the momentum equation. This is fetching the Laplacian term for the Newtonian fluid. And then it is using the source term as well. And then after that, it is solving for momentum predictor equation by solving this pressure Poisson equation. So all those algorithms, I will not go into detail for now. It is what I'm saying is it is just freely available. If you want to add certain other equations that needs to be solved along with it, let's say any transport equation, you can code in the similar fashion using FPM and FEC classes of DDT and divergence terms. So all in all, this code has become quite symbolic. You just need to specify the equation, what you need to solve, without worrying much about the traversing in the I direction, J direction, what we do typically in the Fortran or .c files while we build the code from scratch. So all you need to worry about is you need to have a basic understanding of what the governing equation is, and you can directly implement in the particular applet application such as simple foam, and then use it accordingly for your convenience, and then do the validations and all those things that we are going to do in the upcoming evening session. So again, this is simple foam algorithm, which is steady state incompressible solver. Another class of algorithm that is available is icofoam, which is based on piezo algorithm. So it is applicable for unsteady kind of problems where time is playing the important phenomena, where flow is evolving with respect to time. If you want to have the simulation with respect to that, you can use this icofoam. Again, another advanced version, which is mixture of simple and piezo algorithm, is pimple foam, which is, if you go one step back, so all the dependencies, all the algorithms is coded inside this pimple algorithm. One more thing that you must take care is, if you have noticed, inside every folder, pimple foam, simple foam, whatever algorithm is there, there is always one make folder. So inside this make folder, if you see there is always a file option, a file and option. And if you try to open it files, server is bit overloaded, so it will take a time to open it. Okay. So what it will do is it will look for the .c file in which you have coded your algorithm. So it will look for pimplefoam.c, which was outside. Just I have opened it right now. And then what it will do is this is particular directory where your code after compilation will go, and the name of that code would be pimplefoam. It's as simple as that. And another another file to look is the option file. So whatever .h file it was fetching earlier, whatever has been written in the src folder that I've already explained you. So for dynamically linking while during the runtime, for if you don't need to write the code, otherwise what you have to do is inside .c file you have to write all the codes from the beginning itself. So I want to reuse the codes. So all the reuse locations, whatever coded files you need to specify the path for that, and that path is specified in the option file. And if you need to link certain extra directory into that, you can always go to that particular directory, do the pwd command, and then you can fetch all the .c .h files that has been already coded. So you can basically, what I'm trying to say is you can merge different solvers called together. Let's say if I want to solve the energy equation, and if one of the energy equation is already available in the heat transfer kind of application, so you can link those particular files over here using the make option folders, make option file. Over here, this particular is libsrc, the src directory that I've already told you. So finite volume is basically takes care of all the discretization, the traversal which I was talking about, I, J, K, and all those things. So all the particular all the files that is available in the finite volume is being fetched over here. So you need to have a bit of understanding on how things are going on. You can always go to the online version .esi or .com or .org and type the name of the solver. It will show all the dependencies. If I go, this is for 2112 version. So again, this all files are available online. You can always have a look into that as well. So over here you see like there is a tree dependencies. In C++ we have concept of inheritance. So from what solvers these are being inherited. So all these diagrams are basically available in this API user guide, right? You can always refer back when you are trying to customize your solver. It is a very great help. You can look all the methods, all the functions, all the variables that has been declared in this particular class. And then we create the object and then we fire the codes. So all those class declarations and every methods are available over here. You can always look in how the inheritance concept works over here, polymorphism concept work over here. So due to lack of time, it is very unfortunate to discuss everything at now. So the basic idea over here is OpenFOAM is basically a bunch of codes stitched together using these dependencies. And whatever,
Sir?
if you need to customize the solver, you
Sir.
can always adopt that, make changes accordingly, and then use the compile commands, wmake and wclean, all those commands, and then you can get your own customized solver and use it accordingly to your research purpose. So this is the basic gist of OpenFOAM, all the case directories. And in the subsequent tutorials, what we shall be doing is that is a bit more,
Sir?
is
Can I
bit
ask
more
a question?
practical. This is just was theoretical, setting up all the things over here. So we will be solving lid-driven problem, which is a hello world kind of code when we encounter a new programming language. So lid-driven
Sir?
cavity is the first starting point for the CFD applications. And after that, we will be trying to solve the oscillating cylinder case as well. So and
Can I ask you a question,
this
sir?
was all about the OpenFOAM case directories. And for the installation, I've already sent you a link, a Google Drive link. And inside that, if you see, there is a text file which says, I'm sorry, I'm not able to open it right now. I should have done that. There is one text file that,
Sir, I
that
have a
gives one
question, sir.
particular link of how to install OpenFOAM inside your laptop or desktop, whatever you're working on. And you can follow the steps step by step. That is just copy paste command. If you don't do mistake, if you don't do any error, hopefully you will be able to successfully install OpenFOAM and start using it. So
Sir,
we
I
have
have a
not done
question,
it
sir.
for now. OpenFOAM has already been installed in the Param Shakti cluster a priori. Just what we are going to do is we are going to fetch it. If you do CD and then hit enter, you will directly go to home. No need to do CD ... and go back, very long back to the step. So after successful compilation of the OpenFOAM, you have to source the environment variables of OpenFOAM into the current Linux in which we have logged in. So this is a bit kind of so you are basically trying to open the bash RC file that is present in the current home of the test user 1, 2, 3, or 4, or 5. So if you open this, what we have done is we have already loaded all the modules that is necessary for running OpenFOAM. This has been already implemented. This has been already installed by Param Shakti maintenance persons at IIT KGP. So what you are going to do is we are simply going to source the bash RC file that I have already explained in the beginning, like while setting GCC and PICH, and all the environment variables of the OpenFOAM will be available in this particular Linux terminal. So after setting that, I've already set that in particular accounts. I'll just check once if everybody is able to do it. And after that, you just need to write source tilde.bashrs. So if you type which, let's say if I want to use the simple form solver. So you write which simple form, it should hopefully show the path from which it is being fetched. We'll be using OpenFOAM 6 for the demonstration purpose, the .org version that we have already installed. I'm not going to talk about .esi for now onwards. That was just for the demonstration of installation and all those things. So any versions you can adopt, you can always adopt to different version after you have a basic gist of how the code structure is implemented in each of those versions. After having done this, what we need to do is we need to install ParaView. You can simply go to Google Chrome. That is a bit of long file. During the break time, you can try to install paraview.exe file. This is for Windows users. For Linux users, while you compile OpenFOAM, it by default compiles ParaView inside that as well. So I'll be using Windows for now, and I've already installed ParaView. You can just go to the ParaView website. Just search ParaView. So it should hopefully pop up the paraview.org website. So this is basically saying all the features that is available in ParaView. You go to this at the bottommost, there is download option. So any versions, whatever version is stable for you, you need to figure it out yourself. I would recommend to use 5.11 because 5.12 is bit new for now, and that might be bit unstable for many of the older systems. So 5.11 would be okay. You can use any of the file for installation. Preferably use the first one itself, .msi, it's 340 MB file. After you download, you run the installation and just click next continuously until you copy all the necessary files into your local disk C. And after that, if you search ParaView, the window should look like this. So we will be trying to do that now. I will assist you in doing this, and then we can call this off as a session, right? You can use that particular software folder that I've already shared. I have already shared one ParaView version. You can download from that, or you can download from this website, whichever you are comfortable with. Yeah, I'll take up some of the questions from online mode. Sorry.
Okay, so whatever doubts you have, please. Whatever questions you have, please raise your hands if you have questions. Okay, so first let me. Okay, so hello. So test user 1, 2, 3. You will be seeing an OpenFOAM folder in LS, your home file, home's location. In that OpenFOAM folder, whatever he has shown regarding SRC bin, it is there in that folder. All right. You can just check it for test user 1, 2, 3. For test user 4 and 5, since the file is quite large, we are not able to currently transfer it. We will do that up during the break. All right. So this ParaView is for visualization. So the link he showed, you can just download the file, download the software and install it. Okay, we will be needing it for visualizing whatever we have simulated. Next, the whatever he has shown one BAS RC related. So see, those who have Param Shakti, you don't have to install any OpenFOAM related software now. Okay, so Param Shakti itself, there is a OpenFOAM is available in Param Shakti. So Bash RC is, so basically when you just log into your Param Shakti, the set of codes are executed itself, whatever is done in Bash RC. All right, so you can see, so just do VI, just show that command once, VI. Everybody in your cluster in the home location, just type this vi tilde backslash dot bash rc. Okay, you will be seeing this. You will be seeing this file. Just enter. Anurag, once enter.
Please do not edit this file.
Yeah, please do not edit this file. Okay, so what we are doing is basically we are loading whatever modules, whatever compilers, whatever softwares that are needed for us. We are preloading it so that you don't have to do it. So whenever you open your system, your cluster, your login node, this will be already present. So you can see the third line has OpenFOAM. All right. So that means we are saying that OpenFOAM will be preloaded in your login. So test user 1, 2, 3, 4, 5, they will be having this. So how can you verify it? Okay, one more thing to say is that, are you all comfortable with the VI editor? Can you edit the files? Please raise your hands those who are not comfortable with editing files. Then we can, please raise your hands. Then we can show. Then it will be easier. Okay, quite a lot. Okay, so So VI is basically Vim editor. So we can create a file using just saying VI, just Anurag, VI is a something.c file, just create a C. Yeah. So this means we have creating a test.c file. Okay. VI test.c. So this is a command based editor. Okay. So to just to vi.test.c to insert anything, type I. I will recommend please everybody try it, because if you have to change anything in your code files, you have to do it via this only.
Please use different name for your. But
One more, yeah, we will be telling that also. Yeah, right. So first, please do this, okay? Because if you're not able to do this, you will not be able to change the parameters or any settings that are required to run the ParaView simulations. Okay. So first, so this I'm just showing you. Anurag is basically showing you how to edit files here. So do vi test.c is just creating test.c file. Okay. After we have done that, to edit, click I.
so
Press I.
So if you open it by default, it will show the file name test.c. If you type anything, you can't do anything. Right. So for writing anything inside the file, you first need to press I. Then it will say you are in the insert mode. So from there onwards, you can type anything you want.
Okay, so when you're in the insert mode, you can write, you can delete, you can do anything like edit. All right. So after you have done this, press escape. Once, so what after you press escape, you will be seeing that you have exited the insert mode. All right.
It will not show anything over here.
Yeah.
That insert mode is gone now.
So after you have pressed escape, you will be exiting this mode. Then you have to save. For saving is write colon then W is basically writing it. WQ is writing and exiting the file. So if you want to just write into the file and not exit the file, type :W. Okay, so he has typed :W and press enter. Okay, so you can see it is now test.c is written at the bottom, and hello is written there. Now if I want to quit the file, just do :Q and enter, and you have exited the file, right? Now we had written hello in test.c. So if you want to access test.c, just do vi test.c and enter, and you will be seeing that hello is written there. All right. So anyone still having any issues with editing files? No. Okay. All right. So next thing is, in the lab classes, everyone needs to have their own folders. Please do not do your work in the actual files that are given there. So please make your own in the scratch. So currently, if you do PWD, please, what I'm saying, please do that. Okay. Otherwise, there will be a lot of confusion, and will not be able to do anything. So please do PWD and check if you are in home or scratch. If you are in home, okay, home is basically when you enter Param Shakti, what you will be where you will be at that moment is at next. The files are in scratch. So do cd, then cd scratch, then your test user name, test user account name. So you can do test user 1, 2, 3, whatever you are in the currently. Do that and press enter. Now do PWD. You will be seeing you're in scratch. Please verify everyone that you're able to go to scratch. Another option is just do Anurag, go back to home once. Yeah, do cd scratch in all caps. Yeah, scratch in all caps. Okay, enter. Now do PWD. So you're also in scratch here. So there are two ways. You can do cd. So scratch basically, where $scratch is saying we have saved that path in the scratch name, scratch variable, right? So first one is we are giving the path itself, scratch test user one. Second one is basically scratch is saved, scratch path is saved in that variable, scratch in caps. So CD that will give you that will send to the folder scratch location itself. So here if you do ls, so here if you do ls, you will be seeing which one?
NSM KGP.
NSM. So you will be seeing NSM KGP, or you might be seeing NSM workshop. You might be seeing OpenFOAM KGP. Okay, those who have, please raise your hands if anyone is not finding any of these folders. Okay, just escape.
Lot of questions online. Regarding installation, they are not following up very quickly.
Of this combination of folders, NSM KGP, OpenFOAM KGP, NSM workshop. Please raise your hand and verify which test user that is. Scratch. NSM KGP, NSM workshop, OpenFOAM KGP, OpenFOAM. Search for all these combinations. If none of this is there, please raise your hand. Those who are able to find it, please raise your hand. Okay, so I'm repeating once more how to.
Sir, audio is gone. Please check.
I to insert, I to edit, Q to quit, W to write, and press escape before doing any of this. Okay. Escape, and obviously this one is colon and this one is colon. So those who have, so okay, better to do this. And safest option is, okay, safest option is this, WQ exclamation. So some might have inserted or edited it, but they are doing Q. Just Q. This exclamation is basically forced exit. Best is doing this. Escape, then this. All right. Okay. So those who have seen this folder combinations NSM in the scratch, please be in the scratch destinations, and NSM workshop, OpenFOAM workshop, NSM KGP, anything like that. Is everybody having that in their? Okay, test user one, please raise your hand. Test user one, is it there? Test user two, anybody using test user two? Is it there? Test user two, OpenFOAM KGP, files are there inside. Does do CD and files are present. Okay, okay, yeah. Inside that files are there. Test user 3, anyone? Anyone using test user 3?
Yes, NSM workshop.
4?
Yes.
5? This side should be using test user 4, 5, right? Yeah, this side please use test user 4, 5. Because to use test user 1 and this is test user 3. Okay.
Please keep the accounts separate so that it will.
Yeah, next. So, see, everybody please in the Scratch folder, please create a folder with your name. Okay. So Anurag will be showing you. So any doubt till now, please raise your hands. Scratch pen. So everybody please create your own folder in Scratch with your name.
For making a folder using Linux command, the command is mkdir. This is make directory. From where? So I've just demonstrated. This is the directory that I'm working on. You are inside Scratch, right? I've not demonstrated anything yet. What I'm saying is you need to make a folder of your name. If say your name is XYZ, the command to make a folder is mkdir. My name is Anurag. So I will type mkdir Anurag.
Yeah. So please everybody make your a folder with your own name.
This is
inside
very essential.
Scratch. Okay, because if you don't do this, you will be editing your other script and they will be editing something else and will be running different cases and different parameters and everything. Okay. So make this inside Scratch. So your PWD ones. So at this position, just inside Scratch, you will be making your folder with your name, mkdir, mkdir, whatever your name is. Please confirm that everybody of you have done this. So that in the lab session, we can just start directly with the codes.
Does anyone have similar names? I mean, that will be conflicting them. It is very difficult to find.
Okay. Write your name and your birth date, something to like that. Okay.
Then after you type the name of the folder, hit enter. It will not show any output. But if you do ls,
Correct.
it will show up a folder something like this, right? So if you want to change the directory to your respective folders, don't mess up with the others folders. You just work in your own directory. Otherwise, it will be very much conflicting. If one is changing, other parameters will get changed and you will not be able to do anything. So
okay, one more issue is anybody having an issue with creating their directory because some are getting permission denied. Okay, those who are getting permission denied, you can create the folders at home. How many are getting permission denied? And how many of them are test user 1? Test user 1. All permission denies are from test user 1. Anybody from outside test user 1 who is getting permission denied? How many of you have created the folder? How many of you have created the folders? Okay. How many of you have got permission denied? And how many of you have not created folders? Okay, so only you are. Okay, those who have issues with permission denied, go to home. So for going to home, do cd tilde, cd space tilde. This is for those who are having permission denied error. Go to your home and create the folder. cd space tilde, just do that. It will be at home. Do pwd to verify. You're at home. Then create your name folder there. And those who are creating at home, please remember that your location is at home. So we have to copy the files from the NSM workshop, OpenFOAM, KGP, whatever the location is, to your own folder. Okay. So remember that those who are at home, your location is at home. Destination will be at home.
In the lab session. Shall we do it in the lab session? Because that is the master folder that I'm carrying. It is not present in everywhere. I've just shared it on the Google Drive. If most of them will not find it, then they will again ask question that this folder is not there, this folder is not there. Yeah. Okay. Okay. So we'll just copy. So we will just copy one case, cavity one, right? Cavity.
Start is better to
Cavity and oscillating cylinder. But most of the, like, if you go to NSM,
let's start with the folder, and
then that parent directory will change, right? It is located in some different directories. If you go to NSM KGP, there is Day1. It will work independently, but directory structure has changed. I have made a generic folder, and from there they can fetch those particular things. But in the previous version that I have shared already, that was half-baked. So
let's show one.
Just show on the demonstration. Then we will make it uniform during the breaks. Right?
Okay.
Test user.
Okay, so we will be just showing to how to copy the folders to your own which files to copy and how to do in test user for test user 1. Others don't worry, just observe what is happening. Okay, just write down the steps. So Anurag.
So for copying a particular folder, you need to write cp -r. That it will copy recursively all the contents of the folder. And if you want to copy file, don't write -r. If you write it, it will not create any problem. So always it is safe to write cp -r. And then inside NSM KGP,
Everyone, please observe this because you have to copy the files. Okay. So for test user 1, we are showing. So test user 1 will be having this NSM KGP folder in their scratch. All right. So CP is basically copying the files. -r is for copying folders. Okay.